All right, everyone. Welcome to a new lecture in your embedded systems. Today, I'm going to teach you guys embedded software development. And this lecture basically covers these few sections. We're starting from the steps of developing a program. It is a program for a microcontroller. And there are some ways of designing a program. So there are standard ways rather than like just starting from the scratch and just coding, and that's not the way how it should be. So there are standard ways, so we are following the standard ways. And then we move into the basics of the C language. I hope you might have already learned the C language programming in your first year. So make sure if you are not familiar or if you have forgotten, just refer to these lecture notes because I'm not going to teach you in detail about C programming. But when it comes for microcontroller programming, we are using C and sometimes C++. Make sure you have gone through your all previous lecture notes in the C programming, these conditional statements, functions, and everything, right? Otherwise, it will be hard for you. So you will be look at somewhere else. I will be in some other stage. So I'm just following the people who are following me, and if you are not following me, so that will be a problem of you. So make sure you have gone through all these pre-requirements. I'm just brushing up the basics and just showing you these things that you need, but I'm not covering in details. So make sure you guys spend some time and go back to your first year notes and refer to those. And there could be some other online resources. So it is hard for me to teach the C from beginning and within this 13 weeks lecture series, right? So we are just moving forward with the hardware and all the other peripherals. So C language is something you should be, I trust like when you come to this stage, you should be able to write a program in C. And so some sort of C operations and standard C libraries basically used in FL Studio. All right, let's take a look at the key steps of developing a program. So computer programs are a little bit complicated. It could be a few complicated programs or very simple programs when it comes to microcontrollers. The first step is you have to analyze the problem. So there could be a problem so that you have to find a solution. So sometimes the design engineers will come up with the idea. So the microcontroller based system or embedded system would be the ideal case, right? So sometimes it won't be because I have last week I have taught you because some problems you can just get rid of using some kind of simple analog and digital electronic blocks, or maybe simple like a logic circuit. But if you figure it out, this is the right way of using an embedded system for this problem, then you have to design a program for that, right? So you have to have a clear idea what is your problem. So without knowing your problem, you can't find a solution. So you have to analyze the problem and specify exactly what the program is required to do. So your program should be able to perform different tasks. So that tasks should be able to solve the problem. And you have to specify your inputs and outputs and possible algorithms. So in the embedded system, there could be inputs coming from sensors, switches, etc. So those readings, they could be analog or digital. You should be able to read them. And you have to have some outputs. They could be digital or again analog, or sometimes communication links like SPI, serial. And you have to come up with possible algorithms or how to solve this problem using a suitable algorithm. So the algorithm is a key part, which means this is the way that you find in the solution to your problem. Otherwise, like if your algorithm is weak, there could be different problems when you run the program, and it won't solve your problem as you expect. And then you can design the program taking an overview of the problem. So you know the problem, then you have overall idea what you have to do. And the most importantly, as a design programmers, so always when it comes to embedded systems, modular programming is more preferred, because modular programming is like you have your big program like this, and you one part of the program, you define the functions to read the data from a sensor, and there's another function that perform like communicating to a external device, like this part is individual from this part, this segment, right? This function and this function are individual, so they can do individual tasks. So you can test them separately, like for example, reading data from a sensor, it doesn't affect this communicating with the other devices, right? So you write a function to read the data from this sensor, and you test this individually. So this code is independently to perform one task. And the second task would be to communicate some sort of data to an external device. So you can test it separately, rather than like writing a whole program as like a whole bunch of program and without having segments. So it will be so hard to test them individually, right? And so use modular programs always, so they can be, because if you know the problem, you can divide it to segments or functions, and this they can perform different tasks individually. And like I mentioned, each module can be designed, coded, and tested independently, like write the function. So when the function is called, that will do a specific job. So you can test it separately without worrying about the rest of the program. So finally, when you test all these modules or the segments, when you're happy, so you can combine them and you can order them in according to your algorithm. So that will do in order, like doing this segment first and the second segment as the next stage. And based on your algorithm, you can see how you can combine these modules. Right. So the important and why we are doing this, because it is easy to test the program without affecting the overall code. And so when your module programming is done, so you can start this whole program, like you can do the coding, and you can modify whatever the segments you've written. And then you can test it and see whether how it works. And once you're testing, you can see the syntax errors. Sometimes the compiler, when you compile it, when you build in the code, so it will show pop up syntax errors. And so you have to rectify and go to the particular lines what the compiler shows and see whether there aren't any syntax errors and rectify them. And there could be some runtime. So your code is compiled, built successfully, and you just burn it to the microcontroller and it is running. But when you run, you are getting some kind of errors. I mean, getting data from the sensor, it is not the one that you expect in you want the temperature to be like you have a reference temperature meter. Sometimes let's say you have a temperature thermometer in your hand, like it shows like 30 degrees, and you have a temperature sensor mounted and you are testing it now. This is a sensor, so it gives some data, right? So when you can convert and see, and you will get like a 70 degrees or something, right? So this is the room temperature, but you get in 70. So there is some kind of like a runtime error, like a logical error. So maybe you are the calculations that you have written, maybe there is an error. It's not like a compilation error, right? Systematic error. It's like a logical error. Maybe you have your equations are not accurate and some sort of problems are there. So when you figure it out, you have to rectify that. And sometimes the logical errors may be like it is not running as you expect the order, and there could be several errors. Finally, there could be some bugs. I mean, like you are getting good results, but when you run it for some sort of periods, there could be some kind of bugs popping up. Bugs are there because they are like hidden bugs. They are troublesome. Basically, it just like it won't give you the results as you expect, right? So finding bugs is a little bit difficult, but when your program is used by a external party, they might report it. Your clients will report, and then you will have to go and see and rectify the bugs and remove the bugs. But the bug removing should be done at the level that the designer's level, not rather than when you sell the product. But as everybody knows, like even the Windows, they also have the bugs, and in the once they sell, they get bugs and reported by the customers, and in the next version of the Windows, they clear the bugs and like that. So bug removing is always there. And the documentation is always good practice as programmers. So you can put some comments in your code, and that will explain you the what this function does. And likewise, and that's a good practice, right? So if you leave a company and you leave your code, and if someone else will come to do the job and he has to understand your code, and if you don't have any comments, like the life will be hard for that guy, right? So make sure you will comment and keep some recordings, and that will help your juniors as well. So when you have a team working, so some part of the code is done by you, and the rest of the part is code is done by someone else, and you work as a team. And the team members has to look at everyone's coding, and so documentation and committee will be helped to as a work as a team and speed up the process rather than explaining everything. Yeah. Okay, right. Now let's talk about the design method. So before you design your program, before you move into the coding, it's always to design your algorithms, right? So the algorithms could be either comes as a flowcharts, records, state diagrams, design structure diagrams, data flow diagrams, and set schemes. But most widely used methods are flowcharts and state diagrams and design structure diagrams in the embedded systems. But when it comes to software development in other computer software developments, you can get pseudocoders and other types. But we are interested in flowcharts, state diagrams, and design structure diagrams in this lecture. Okay, so if you take a look at the computer program, there are three basic programming processes. So they can be identified as sequence, selection, and iteration. Sequence is the order in which operations must be carried out. For example, like you can say, do this first and then do the other one and other one, likewise, like the order, right? There should be order in your code, like otherwise you can't run this task first and the other task second. And if you don't have order, like it will be jeopardized, which means like it doesn't work as you expect. So sequence is like do this first and this, and likewise the order. And sometimes you might see like the selection is also required, choices that are made in solving the problem, programming problem, like a if-else diagram. Like if this happens, do this like a true. If it does not happens, like false, like if-else statements. If you can remember in your program, like choices, like, and the cases like do this one case and do this another case, like a switch statements, right? And finally, the iterations or the loops, for example, like a while loop, until the or while some condition is true, stay on that loop and do this job, or until something is true or false, do this and wait and repeat it. And now if you use a for loop or something, like do the same thing for x times, like you have seen like a for loop, like integer I is equals to 0, I plus plus, and you can remember the for loops, like you will do it for a number of times. And finally, wait for an event. Again, like if an interrupt happens, if something external would trigger the microcontroller, so you can jump to that event and wait for that event. If the event happens, so do that task and come return back. For example, now you are reading a newspaper and a telephone call comes, right? So you will go and answer to the phone call. And when you've done the answer into the phone call, and you keep the phone there and you return back and just starting the reading unit, right? So you are waiting for until the telephone rings, and once you complete it, and you return and do your normal job. Structure diagram symbols are like this. This is used for terminator, like indicate start and stop of a flow chart. And this is for decision, like if this happens, something like that. So we use for decisions. And for actions, we use this rectangle, and for inputs, we use this one. So in order to connect several sections, we use connectors. Okay, then we can move to the structure diagrams. The first one is designator, which means like you have to write something, label it, place the designator anywhere on the diagram or designator subsections on the program due to the further refinements. So it will help you to identify what is that, and use to mask start and end of the program. So if you have a start and end of the program, so then use designators. And the processes, use of sequential statement, which will be executed and then go on to the next statement. So this is a one process, like after this start, do this job. And if you have another job, you have to again use another rectangle. So that represents something like read the data from the input A, or like write data to the output B, something like that. And there are some decision elements like if else. If means like if this condition is true, do this task, right? If this is yes, do this. And if you have if else, if this condition is true, do this. And if it is false, do this, like if true, this, else, this, like that. And switches statements, if you can remember, like you have a variable, that variable is copied here, and it is compared with these values. Like, for example, if this value is equals to 1, do this. If this value is equals to 2, do this. Otherwise, as a default, do this one. If you don't have else, it will just return. Like if you're getting some like data updated from a sensor, that value is let's say 2. So the value is here 1. So it just skip, and the value is 2, which is equals this, and then it will do only this task, right? If you get number 3 or something, like it is else, So it will do the default task, or if you don't use else, it won't do anything and it will just return. And you can find some loops as well. The while loop is you check the condition and waiting, and if this condition is true, you will do this what is linked to this line, right? So there could be some sort of task linked to here. So the thing is, like, you just check the condition first and then execute this one, right? In the do while, you execute your process first and then you check your condition, right? So at least if the condition is not true, you will do this for one time, and once the condition is not true, you will skip. So do while is you first do the thing and then check and wait in the loop. Here you wait in the loop, and if it is true only, you do this. And for loops are, you might have already known, they are repeated statements for a number of times and to perform a task. And there are some other diagrams for function calls. So you can call a function, and there could be connectors to connect to a different page. Like if your diagram is too big, and if you want to document it, you might need to refer to another page. So if you want to go to another page, you can use this connector and to page number maybe 2. And if you continue from page number 2, like if you open the page number 2, so you have to have some sort of like a connecting back referring from page 1. So they know like this is coming from page 1 and we are starting from page 2. And if you are in the same page, you don't need to put the page number and connect it to the location like point A and point B in the same page. Okay, now we can take a simple example, which is the state machine. So state machine is another alternative way for structure diagrams, sometimes flowcharts. So one simple example I have selected here, which is a turnstile. Turnstile is a gate barrier, so to pass the people, to control the public action. So if a person comes here, someone like comes here, so this is your pathway, right? So the turnstile is in here, so he can't move because it is blocked. So if it is released and this one is rotating like a clockwise direction and letting this guy to pass there, and then it will again lock this point, right? So when it is open, it is free, like this guy can just push this one and it will just freely rotate and he can just pass there. And once it is locked, no one can move through it. So in order to open the turnstile, either like they could be in the public transportation service, you have to use your bus ticket or train ticket and you just scan it, and if it is identified and if it's a valid one, so it will let you to pass through to the train station or the bus. And sometimes you can insert some coins. So this example I have used the case of a coin, which means when you insert a coin, it will open and let you to go through it, and then it will automatically close. Okay, so initially the arms are locked. So this is a locked position, so no one can move through it. And if someone put a coin here, so it will free this lock, and this one can rotate, so the person can pass through. After the customer passes through, the arms are again locked. And there are two states in this turnstile, right? The first one is the locked state, like it's normally locked. And the other state is unlocked. So if a coin is inserted, the other state will be unlocked. And the inputs, two inputs are there. So one input is adding a coin, and the other one is pushing this arm, right, by a person. So we can construct a state transition table based on these two states. the current state. Let's take this one is locked, and the second one is unlocked. And once you are in the locked state, we can have inputs and the outputs and the next state, right? So when the turnstile is locked, if you add a coin as the input, so it should be unlocked, right? So it should be unlocked when you add a coin. So your input is coin and the output is just to release this turnstile so the customer can pass through. And so it is the next stage will be unlocked, right? Then so when this is locked and if there's no coin is inserted, and if someone comes and try to push without adding a coin, so the input is pushed, so he's trying to push, but nothing will happen, right? So the next state will be also locked, right? I mean, when it is locked, when a coin is at, next state will be unlocked because it has to be unlocked, which means your output is open. And when it is locked and when no one is putting a coin and someone push it, the next state will be again the locked state, right? Nothing will happen to the output because without a coin, when someone try to push, nothing should be happen. If you are in the unlocked position, which means like now you have inserted a coin, and so you have added another coin, right? Someone mistakenly added another coin. So the output should be do nothing, like it is unlocked, and adding an additional coin will be also in the unlocked position, right? So unlocked and again adding a coin is unlocked. So if you are in the unlocked and then someone push, so the customer passes, and then the next state should be locked. So you should lock it again, right? When the customer pass through, so this turnstile should be locked, otherwise more people will pass through it. So this is the state transition table, but it is more convenient to have state diagrams like this. When you construct the state diagrams, the states are represented by a node, like a circle, and the transitions from one state to other is represented by edges or the arrows. Now this is the start point. So when you turn on the machine, it is initially locked, right? So this is the start, and it's jump to the locked state, and then this is the powering up state, and then jump to the locked state. And once it is locked, if someone try to push, again it is locked, right? Nothing should happen. So it is in the locked state. So if someone add a coin only, it will change its state. So someone put a coin, so it will go to the unlocked state. And again, someone put a coin, so it should be again in the unlocked state, right? So, and if someone push and this one, so it will detect it as a push and let the person to move. After that, the transition is move back to the locked position. So this is similar to like designing a flow chart or algorithm. State machine is also one way of developing your algorithm. So if you have this one, you can write a code, and if you have this one also, you can start writing your code because now you know the solution for your problem, right? All right. Now we are moving to the C programming basics. So there are 28 keywords that should not be used when you're defining any functions. So when you're defining your own functions, do not use these keywords like a do, for, if, int. So you can't use them, right? So when you're doing the modular programs or when you're defining new functions, do not use these names. So that will make some compilation errors. Right. So in any microcontroller program, so there's a main function. So you know in C programming, there's a main function. So the main function does not need to be appear exactly at the beginning of the program. It can occur anywhere. So this is a very simple code written in Atmel Studio. So first you have to include insert this library. Then the main function is does not return anything, so it's void and main, and the return is also void. This argument is also void, so it doesn't take anything, right? An input. And once you jump into the main function, there's another function called setup. So that is to initialize the inputs and outputs of a microcontroller. That's why we use setup function. So once the main function calls, it will do this job and go to the setup function. This function is called. And in the setup function, so it doesn't return anything or it doesn't take any argument. So it is void. And what it does is like DDRC, so like a port C of the microcontroller, it has all as outputs. This port will become output because this 0 into FF means 255, which means all ones. And you can initialize some variables, like a counter variable is initially at 0. So once this is done, it will comes to here, and sometimes there will be some while loops, and you don't need to set up it again and again. So we will learn this C programming language more examples when you move to the next lectures. But the thing is, like any code should have some main function. So it is the way the first point that the program jumps and executes. And there are several variables that you can use when you're coding. A variable is an identity that can be assigned a value, where the value may be modified in the program. So you can define a value to the variable. So you have to define the right value, and that value could be changed once the program is running, maybe updated by a sensor, something like that. A variable name cannot be the same as the keyword of or a function. Like you can't use that the 28 keywords in the variables. A variable name cannot be the same as the keyword and a function name, right? So these are some variables. Like a bit is like if you define bit, that variable can have only a single bit, right? It can be either 0 or 1. The variable type is bit, which the value can be either 0 or 1. Boolean or bool, bit width is 1, and it could be true or false. So either you can use a bit or bool. Bool is you have to define it as either true or false. And this is a special function register byte. That's a bit one. And char is like a character from 0 to 255, 8 bits. Short is integer, 16-bit. Long is integer, 32 bits. So these are the values. So they are signed integers. Integer is could be either 16 or 32, depending on the compiler. Floats and doubles are real numbers. The float, you can go up to 6 decimal digit precision, and in the double, it's 12 decimal digital precision. And variable can be local to a function, or global, access to any function in the program, or argument of a function parameter. Like when you call the parameter, you can inside the brackets, it could be an argument. And all your variables must be declared before they are used. So at the start of the code, you have to define if you use a variable, like a variable name, like a count, loop, resource, or anything, you have to define what is the type, right? Otherwise, compiler will just not understand. So if you use a temp as a char, so you have to use char. And again, this final hash resource, this one is like defined as signed long. So there could be different variable names, not like the 28 keywords, and you can define the type based on your requirement. And we also need to use different number bases when we using the Atmel Studio. If you use the binary number base, you have to define the number as starting from 0B. This is how the compiler know it is a binary number. But it is obvious, like if someone write this, it should be binary, but the compiler, the way that in that Studio is like you have to add 0B in front of this one if it is a binary number. So this number represent 85 in decimal. And if you want to define a hexadecimal number, you have to add a 0x, right? And then the hexadecimal number. So FF means like a 511 in decimal. This is how you define this in the Atmel Studio. For decimal numbers, you don't need to add like a 0B or 0x, anything like it. You just type that number, right? So if you want to convert between these number bases, use this link. So there could be other links as well. So you just can convert a decimal to binary, binary to decimal, or anything. Or either you can use your calculator as well. And these are the key C operators. There's subtraction, addition, multiplication, division, modulo division, decrement, and increment. And there are some logical operations. The logical operation byte-wise. Byte-wise mean like a single byte, 8 bits, right? So if you have AND, so that is byte-wise AND. And if you have OR, that is byte-wise OR. And if you have this symbol, it is byte-wise NOT, right? And so it is applied to whole byte, because you have to consider the whole byte. Likewise, this number, since it is more than 1, it is considered as true. And this number is 0, and it is considered to be false. So I have a few examples, like N1 is a number. So this number represents some kind of a decimal value, which is more than 1. So it is true. And this is again true. And N3 is 0, it is false, right? So N1 and byte-wise with N2, this is 1. Whole bit is more than 1, which means 1. N1 and N2 is again 1. So and 1 and 1 is 1. N1 and then N3 is 0, it is 0. N1 is 1, N2 is 1, N1 or N2 is 1. N1 or N3 is again 1, right? So you're taking this whole number. If it is more than 1, it is 1. If you take this whole number, if it is 0, it is 0. And bitwise operations are like you apply to single bit, right? So these are the bitwise AND or exclusive or one's complement and shift right and shift left. And so this number N1 is like this, and N2 is like this. So if you take N1 and N2, so you have to take single bits separately and do this task like that. You take this one and this one and take the AND, right? So this results has come from AND of this two, right? So this is 1 and this is 1, AND of that one is 1, right? And if you take this one, this 0 and this 0 and 0 and 0 and this 0, right? So likewise, you have to apply to every single bit and you have to get the result. So that is why called bitwise AND. And bitwise OR will be the same. So you do the OR operation for each bit and you will get the results. And complement this, you just invert that number. Like here it is 1. Once you get the complement, like a NOT, that is 0. So 1's complement is 0, and here 0, this will be 1. Like as you invert every bit, right? And N2 shifted to left 3 times. 3 means like 3 times you have to left. If it is 1, you have to shift 1. If it is 2, 2 times, and if it is 3, 3 times. Now N2 is this number. N2 is this number, right? So you have to shift it to 3 times. So when you shift it, these 3 should be go out, right? These 3 should be go out. And this segment is now shifted to here, right? So now you can see like 0, 0, 1, 0, 1 will be here, right? Because these 3 go out. And now you know, like this is 5. There should be some, because it's a 8-bit number, like a byte. So the rest of the bits are filled by zeros, right? This is that part. So you shift it to right, and these 3 goes out, and these 3 move to this side, and the rest is filled by 0. And right shift, it will be the same. If you right shift to this one, so 3 times, this 3 will be go out, and the remaining will be filled with zeros. And there are some relational operations also. So when you deal with numbers, like taking a results from a temperature sensor and compare it with like a value, like if the temperature is more than 35 degrees, turn this output fan on, something like that. In that cases, we have to compare 2 numbers. Then you can use this relational operations: greater than or equal, less than or equal. Equal means like if 2 numbers are equal, you have to use a double equal, right? If you use a single equal, that number will be equal to the other number. So if you want to compare 2 numbers, you have to always use 2 equal signs, right? If you want to check these 2 numbers are not equal, like let's say if you want to check A and B are equal, you have to use check like this, right? If you want to check A and B are not equal, you have to do like that. So if you set A is equals to B, if you want to check, like A will become B, right? This is not how you compare. So this is wrong. So this is the right way of comparing numbers, whether they are equal or not equal. And when we deal with this C coding, you have to use libraries, because the libraries are important. So if you don't have libraries, the life will be hard for the programmer. So he have to define his own functions every time. But the compilers like Atmel Studios, it has different libraries inbuilt that comes handy. So which means like the life will be easy. We can use the standard libraries to read the data or communication or do some math functions. So the libraries are like, first one is the stdio.h, which is the standard input output library. So if you're defining your inputs as the microcontroller, you have to use this library. And if you have some arithmetic operations, always use math.h. It has plenty of mathematical functions. And if you want to make a delay in your code, this is how you define the delay. Delay hash ms1000. This is the not. This is slightly different from the way that you define delays in Arduino. This is for Atmel Studio. If you want to define a delay in milliseconds, this is how you define. If you want to define the delay in microseconds, this is how you define it. But you have to include the utility hash delay.h library, then only it will do the job. But at the same time, you have to define your CPU speed, clock speed, right? So you have to include this library, and then you have to define what is your CPU clock speed. Okay. So if you do these 2, then only you can use delay function. Otherwise, the compiler will generate some errors. All right. So that's all for this lecture. So it's a very basics briefing about C programming and this introduction to these libraries and how we make an algorithm in a C program before we writing a code. So next week we are starting this writing simple codes in Atmel Studio to do specific task. So this is the end of this lecture. Thank you for joining. So in next week we will move. I will introduce you lecture. So that is it.